Okay, in this video, we are going to look at building a MOSFET bootstrap circuit. Now there's two power MOSFETs that I use in my projects and that I stock. One of them is the IRL Z44N. Now the L in the part number means logic level. So we could drive the gate to source with the output of a 5-volt microcontroller, and we could turn this MOSFET fully on. Now the other part number, IRLI Z44N, you can see here, the I means insulated. So you can see on this tab package, the tab is plastic, so it's insulated, so I can bolt it to my enclosure, and I don't have to worry about shorting out my drain. Now the specs on the IRL Z44N, it's an N-channel MOSFET. The RDS, the drain to source on resistance, is 22 milliohms, and the CISS, that's the gate to source capacitance, is 1700 picofarads. Now the other MOSFET transistor that I use is the IRF 1405. Now this is not a logic level MOSFET, so you have to drive the gate to source with a 10 volts to drive it fully on. It's an N-channel MOSFET. The RDS, the drain to source on resistance, is 5.3 milliohms, and the CISS, that's the gate to source capacitance, is 5480 picofarads. So the IRF 1405 is actually an automotive spec power MOSFET. So I like using the automotive specs in all my projects. So that's our worst case design. So that's why I picked the IRF 1405. Now normally when we use a MOSFET, we use it in a low side switching configuration, but sometimes we need to have a high side switching configuration where the one side of our load is grounded. Now to use that with an N-channel MOSFET, we need a bootstrap circuit. So in this video we're going to look into how we could build a bootstrap circuit so we could use a high side switch configuration with an N-channel MOSFET transistor. Okay, here's a schematic diagram of a low side switching circuit using an N-channel MOSFET. Now one side of the load is connected to the power supply, plus 12 volts. The other side of the load is connected to the drain. Now when we turn on the MOSFET, the load will get its ground through the MOSFET and energize the load. Now to turn on this MOSFET, we apply a positive voltage to the gate between the gate and source. And for the IRL Z44N, which is a logic level MOSFET, we need a 5 volts at the gate to turn on the MOSFET. And for the IRF 1405, we need 10 volts at the gate between the gate and source to turn on the MOSFET. And when we do that, we'll get a RDS, a drain to source on resistance of 5.3 milliohms for the IRF 1405. Okay, here's a schematic diagram of a high side switching circuit using a P-channel MOSFET, an IRF 9630. Now you notice one side of the load is connected to ground, the other side of the load is connected to the drain. Now the gate and the source are connected together through the resistor, so they're at the same potential, so the MOSFET transistor will be off. Now to turn on the MOSFET transistor, we ground the gate, so now we'll have a voltage difference between the gate and the source. It'll be 12 volts. It'll turn on the MOSFET. So by grounding the gate, it puts it to 0 volts, so it'll be more negative than the drain. It'll be 12 volts more negative, so it'll turn on the P-channel MOSFET. Now when the MOSFET turns on, it's going to energize the load. But if you look at the RDS, the drain to source on resistance, it's 800 milliohms, which is pretty high in comparison to an N-channel MOSFET. So if we're driving a heavy load, we might get some dissipation in the MOSFET transistor. So to solve that, we'll use a high side switching, but we'll use an N-channel transistor, an N-channel MOSFET, so we have a lower RDS on resistance. Okay, here's a schematic diagram of a high side switching circuit using an N-channel MOSFET, so we could have a low drain to source on resistance. Now you notice one side of the load is connected to ground, other side of the load is connected to the source. Now we have one problem with the circuitry. When we enable the MOSFET by applying 12 volts to the gate, it will energize the load, and we'll have 12 volts across the load, so we'll have 12 volts at the source, we'll have 12 volts at the gate. So there'll be 0 voltage potential between the gate and source, and the transistor will be off. Now in order to turn the transistor on, we need 24 volts between the gate and ground. So when the load comes on, we get 12 volts across the load, there'll be 12 volts at the source, there'll be 24 volts at the gate, and that'll give us a 12 volt potential between the gate and source, which will turn on the transistor. So we need a bootstrapping circuitry that will enable us to do that. So with the bootstrapping circuitry, it will give us 24 volts between the gate and ground, and that will enable us to turn on the transistor properly. Okay, I have my bootstrap circuitry powered up on my breadboard. And I'm using an N-channel MOSFET configured as a high side switcher. There's my MOSFET here. And my load is a light bulb, a 12 volt light bulb. You can see over here. And my Arduino Nano is there just to turn the load on and off, to blink the light bulb. So then Arduino Nano is driving this NPN transistor, which is open collector, which is driving the circuitry. Now the circuitry has low parts count. You can have a look at it. You can see there's two resistors, a capacitor and a diode, and then the N-channel MOSFET. So that's all we need for our bootstrap circuitry, and that's going to give us 24 volts to drive our gate on our MOSFET. So I could activate the program to blink our load, to blink the bulb. So there she's turning the load on and off through the Arduino Nano. Now there's one drawback from the circuitry. Now if I turn off the blink circuit, so it's on steady. So right now we're feeding 24 volts to the gate of the MOSFET. So 12 volts is coming from the power supply. Another 12 volts is coming from this capacitor, which is charged up to 12 volts. So the capacitor and the power supply are in series to give 24 volts. Now after a certain period of time, this capacitor is going to drain off. It's going to leak out through the diode. You can see the diode over here. So eventually we'll lose our drive. So this is an on-off type circuitry, like a hammer driver. If you say drive a solenoid, it's on, off. So every time the bulb goes off, it's going to recharge the capacitor. So this is more of an on-off circuit than a steady state on circuit. But it's a low parts count, and we'll have a look at the schematic to see how the circuitry works. Okay, here's the schematic diagram of my bootstrap circuitry, which I built on my breadboard, using an N-channel MOSFET configured as a high-side switcher. And here's my load. It's my light bulb. And if the load is inductive, you could put this optional Schottky diode across the inductive load for protection purposes. Now we'll start out with the load being off. So this transistor will be on from the Arduino Nano, and the collector will be at ground, so it's going to ground out any voltage to the gate of the MOSFET, so the MOSFET will be off. Now this capacitor could charge up now from the power supply through the diode, through the capacitor, and through the filament of the bulb to ground. So the capacitor will charge up to 12 volts. Now when we turn off the transistor, so we take it out of the circuit, now we're going to have the 12 volts from the capacitor fed back into the gate of the MOSFET. So we'll have 12 volts from the gate to the source, and it'll turn on the MOSFET. Now as the MOSFET turns on, it's going to give power to the load. So the voltage of the load is going to start to increase. And as it's increasing, this point will increase at the same rate. Until the load is fully on, we'll have 12 volts across the load. We'll have 12 volts across the capacitor, so they're both in series. So we'll have 24 volts fed to the gate of the MOSFET, which will turn it on properly. And then when we turn it off, it goes back to the same sequence. When the load goes off, the capacitor can recharge again up to 12 volts. So you can see if you keep the load on, eventually this capacitor is going to leak out through the leakage, reverse leakage of this diode, and it's going to leak down. So this is an on-off circuit. So that's my circuit there for my bootstrap circuitry. And I hope this gives you some information how you can build your own bootstrap circuitry to build an N-channel high-side switcher. Okay, now you know how a bootstrap circuitry works. Now normally if you want to use a MOSFET as a high-side switcher, you would use a P-channel MOSFET. It makes it a lot easier. But if you run into the problem where the drain to source resistance is just too high, this is one solution. Also, if you want to turn on your load constantly, you could actually build a charge pump circuitry for 24 volts and feed that into the gate of the MOSFET. But I just wanted to come up with a low part solution. So I'd made this video to give you guys an introduction how bootstrap circuits work.